Welcome back. In lecture 50, we will talk about vehicular emission and pollution modeling. The different concepts that we will cover: introduction to vehicular emission and pollution modeling. We will look into the Indian emission standards, transportation emission measurement technologies, transportation emission modeling, and within that we will look into the IV model, and then finally we will talk about transportation pollution monitoring. So, we know that accurate traffic related emission estimates is critical to air quality assessment, and we need to do air quality assessment to understand the impact of traffic air pollution. And once we know that from air quality we can typically have a understanding about what kind of health effects different levels of air quality will have. So, emissions are the tailpipe emissions from passenger and as well as goods vehicles, and this emission, when it gets diluted in the air, and we find different concentration of pollutants, and that is what we measure in terms of air quality assessment. So, then finally comes the part where we have to also determine what kind of health impacts does different levels of air quality has, but it is very difficult to measure. So, instead what we have got standards, ambient air quality standards, and we try to limit the concentration levels, or we will try to design policies or limit our emissions to such a level so that the ambient air quality standards are not exceeded. So, when we talk about traffic related emissions, the major factors influencing road transport emissions are vehicular fleet composition. That means the different types of vehicles made by different manufacturers and their make and then their age. All these have a role. It depends, and based on each of this type of vehicles, they will have different effect on emission, or they do emit different amounts of pollutants. Then there is of course the vehicular technology involved, like there may be passenger cars, but each car may not follow the same technology. Some has got maybe a hybrid technology, some has got certain kind of motor which is different from another particular vehicle, and so the technologies are different, and that also leads to different amount of emissions. And then engine capacity, that means the size of the cubic capacity of the engine also do have a role in the total emission that is generated. The fuel characteristics of that particular country, or even for that particular area, if it's so that also play a role. For example, amount of sulfur in the fuel and so on. Then physical infrastructure, like for example, what kind of road space do we have got, what is the grade of the road, this play a role in also the amount of fuel consumed, and that actually leads to different kinds of emission as well. And we also have got differences in driving behavior in different areas, and the meteorology also varies from place to place. So, all these factors influence road transport emission. Now, once the pollutants are emitted, the next step is to understand how the pollutant dispersal affects. That means how the pollutants are dispersed in the atmosphere, and that process is also affected by many factors. In fact, it is a much more complicated process. So, the basic, the main impact, the factor that has got an impact is of course meteorology. So, which includes wind speed, wind direction, atmospheric stability, so the boundary layer conditions, and so all this plays a big role. Then the emission height. So, vehicles are of course at the ground level. So, emission height, we are not talking about stacks like stacks from industries, and then geographical features for that particular area, and the source characteristics, like what is it a point source, line source. Point source means maybe it's industry stack is a point source, whereas a road with vehicles on it could be considered as a line source. So, these are the different characteristics, and in addition to that, once the pollutants come out of the tailpipe, it starts acting, or because these are chemicals and they starts reacting. So, this change in the chemical properties also needs to be considered, and then we need to consider its dilution or mixing with air. So, even if we want to measure emissions, we have to consider the factor that it is getting diluted, and then separation or accumulation with different pollutants, as depending on their physical characteristics, get separated or they accumulate, and also settling due to gravity, rain, or any other interception by plants, certain other surfaces, and so on. So, these are the different issues that also needs to be looked into when we talk about pollutant dispersal. So dispersion is often very difficult to model, and it is even difficult if you don't have enough data. And as you can understand, emission estimation is primarily not that difficult to model, but what is difficult is the to get the data related to different kinds of vehicles, different kind of technologies that are in use at this present point of time in road. So that is very difficult to get. And finally, the temporal variations in pollution levels also adds another level of difficulty. So these three tables actually shows the Indian emission standards which are currently adopted. For example, the first table on the left hand side shows the four-wheeler passenger vehicles standards for them. So here the standards followed is Bharat stage 5 right now, and we are now set a date for Bharat stage 6, which is Euro 6, which is supposed to come in which was supposed to come in effect from 2020 nationwide. And so this follows primarily the Euro 6 norms. It's a very stringent norm, and so it's expected that with the application of this particular standard, the amount of emission will come down drastically. And similarly, we have got standards for 2 and 3 wheeled vehicles, which is given over here, and we also have got standards for heavy vehicles like buses and trucks. So similarly, we have got standards for lightweight vehicles, for passengers, goods carrying vehicles, and so on. So here you can see that over here the emission standards are given, and here the emission standards are given in gram per kilowatt hour for this truck and bus engines, because those are big in size. So over here it is gram per kilometer. So in that sense, if you see that the different kinds of vehicles have got different kinds of emissions coming out of their tailpipe. That means a car which adheres to Bharat stage 2 will emit a differently compared to a car which adheres to Bharat stage 4, because here the standards were much more stringent, and so the emissions of the vehicles, the companies must have worked to reduce the emissions. So if we survey a vehicle, or if we measure the tailpipe emissions from a vehicle which is from stage 5 and also a vehicle which is from stage 2, we will find significant difference. Now, when we are trying to determine total emission for a particular city or an urban area, we need to understand that, okay, how many of these particular vehicles belongs to which category. That means that this actually will tell us that what kind of emissions, maximum emissions this kind of vehicle is likely to produce, and also the related technologies that has been used in those kind of vehicles. So that means there is one way to determine what kind of fleet does a particular urban area has, to determine number of vehicles registered during a certain period and under which norm it has been registered. So, and at that point of time, what was the norm in place, and that actually gives us an estimate about what kind of emissions are possible to come out from those kind of vehicles. But this is only one part, but of course it depends upon the wear and tear of the vehicle, the age of the vehicle, depends on many other, how much kilometers it has been driven, what is the kind of technology that the vehicle uses, the size of the engine, all these things also do play a role. But this actually gives us a very fair idea about what is the composition and what kind of emissions those vehicles emit at different times when it was registered. So broadly, when we talk about emission, we have to start about talking about transportation emission measurement technologies first. So how is transportation emission measured? Because as you can understand, each vehicle emits differently, right? It depends on age, it depends on so many other factors. So we need to first understand how the transportation emission is measured, and also our models for determining emission is also based on that. So the first or the most common technology that is used is called dynamometer and driving cycle testing. Now this is the most widely used and the very basic technology. There are two forms of it. One is the chassis dynamometer testing, and the other is the engine dynamometer testing. Now a dynamometer calculates power output by measuring the force or torque and the rotational speed of the engine motor or the wheel of the vehicle. So when it is wheel of the vehicle, then it is chassis dynamometer testing, and when it is directly the engine, we can say it's a engine dynamometer testing. So this kind of testing happens in the laboratory where the vehicle is accelerated or we decelerated or moved in a steady state. That means we run the engine at a steady state and we measure what kind of emission it is giving, right? So what kind of emission it is resulting in, and this kind of tests were done to determine EPA's mobile model. So in the mobile model, what in any kind of emission model, what we measure is the total kilometers driven and how it was driven. That means what was the characteristics of that driving condition, and then also we also determine what was the emission factor related with that kind of driving condition for that kind of vehicle of that particular technology. So over here, this actually helps us to estimate the emission rates at for the vehicle at different driving conditions. So we can change the RPM and see that okay, how the emission is increasing and so on. So so first we have to need to calibrate this kind of emission models. So this actually help us to determine the emission profile of different vehicles or the emission factors of different vehicles and how it varies with different change in different characteristics, and this actually help us to this is the basis of emission modeling. So in case of this dynamometer testing, driving cycles representing different driving patterns and characteristics are analyzed, and this is adopted for emission certification and compliance. But as you can understand, these are held in labs. This requires a big test bed, so it's expensive. It takes a lot of time because the vehicle has to be engaged in that, and so there has been a lot of criticism also for this kind of testing. But this is the most widely used, most popular, and it is used by most of the people. So even though we have adopted other methods, this method still is there. So this is always a complementary method as well. So then we have got vehicle inspection and maintenance programs. Each country has got their own way to generate PUC certificates, as in India we generate pollution under control certificates. So this is a vehicle inspection and maintenance program where the vehicle is inspected for emission. So this is for in-use vehicles. So whereas dynamometer testing is usually when the manufacturer can first produce a vehicle and then do the testing and all, whereas this IM programs are designed by authorities to test in-use vehicles, that what is the tailpipe emission coming out of them. So how do we measure it? We use a dynamometer over here as well, but at the same time we can also use onboard diagnostic systems. So these are OBD systems which are fitted with most vehicles, with all vehicles nowadays, and there if we plug into the vehicle and if we rev the vehicle, then automatically the RPMs and everything is recorded, and the OBD system can tell us what was the engine revolutions, and from that we can also measure the amount of emission coming out of the tailpipe by measuring it separately. So this kind of tests are also based on dynamometer, and also we can use a dynamometer as well. So this is another form of testing, or we can say it's another form of emission measurement technology as well. So the next technology is called Portable Emission Monitoring System, or in short PEMS. It was developed by Environmental Protection Agency of the United States in the late 1990s. So this one is a real-time on-road vehicle emission test, and initially this was called Real-Time On-Road Vehicle Emission Reporter, short form ROVR, or Simple Portable Onboard Test, or short form SPOT. So this was the initial form of this particular test. Now later on it was developed by many private companies as well, and PEMS record emissions while operating on road using onboard emission analytical tools. So that means it is real world driving condition test. So this is not happening at the laboratory conditions, this happens in real world, and it reflects real world conditions. So this kind of test could be done independently, or it could be also matched with a dynamometer test as well. And this actually is very good way of testing, because it can also detect very low amount of emission, particularly from vehicles which are hybrid vehicles and so on. And this kind of test actually show that there is huge amount of disparity between actual test cycles and real world emissions. That means the way a vehicle has been tested in laboratory and it has been certified that this vehicle emits so much, or even it's in a stationary conditions, we just rev it and it gives certain kinds of emissions. But in real world, when it actually rolls or runs, then it actually gives out much higher values of emission. And these values vary significantly, not only for this different amount of acceleration and deceleration and all, but also between petrol and diesel vehicles as well. So nowadays, most of the models are now shifting towards PAMs, or many countries are also going towards this kind of monitoring systems, which would be more stringent, and it ensures that there is compliance to emission norms all throughout vehicle's drive cycle, not only during testing but also during on-road conditions. So finally, we have also got certain other methods which are called remote sensing devices. So here we don't do actual tailpipe emissions. What we do is we do this test without stopping the vehicles. So we set up beside the road. We have a infrared and ultraviolet sort of beam, and when the vehicle passes this beam, we can actually detect that, okay, what kind of concentrations of hydrocarbons, carbon monoxide, nitrogen oxide, carbon dioxide is there in the exhaust that is coming out of that vehicle. So basically, it's the diluted exhaust which is coming out of the vehicle, which actually is measured, and this is based on the infrared and ultraviolet absorption principle. And so this is basically where we don't have to make the vehicle wet. As soon as the vehicle passes, we get a reading for that particular vehicle's emission. But it depends again on many factors. It depends on the environmental conditions. It depends on to a certain extent on the concentration of other vehicles, the background concentration, and so on. So this kind of test is done where not only we measure the kind of concentration, but we also measure the license plate for this particular vehicle. We identify that by taking a photograph. And this kind of vehicles are, this kind of test is effective to test how our existing maintenance and inspection programs are being effective, because most of the cars may show a PUC certificate, so everything is under control, but on road we can see very high levels of pollution. So this is a sort of a second check, and this could be used to generate emission inventories and data for vehicle fleet at very low cost. So these were the different kind of tests that was involved. Now using this test, we actually generate data for the emission or rather the emission factors for different kinds of vehicles in different driving conditions, which is used in transportation emission modeling. So transportation emission modeling is where we estimate and predict transportation emissions coming out of different kinds of vehicles. So usually this model is done both at the macroscopic level or at the microscopic level, or we can also say mesoscopic level as well. Now macroscopic level means it's a regional level. Regional means it could be at an urban level, or we can, or even for a zone level. That means we measure that, okay, how many vehicles are there in that operating in that particular zone, and what is the total amount of emission coming out of those vehicles. So there are two ways to do that. One is called a travel based model and the other is fuel based model. So as you can understand from these two terms, fuel based model means based on the amount of fuel consumed, we can estimate the amount of emission, and for travel based models, we can understand based on the kilometers travel, we can also estimate the emission. And the microscopic models or mesoscopic models are primarily related with individual vehicles, or we try to determine emissions for each and individual car based on their particular driving patterns, based on their usage and so on, and based on the age and the other characteristics of that particular car. So usually there are two ways to get the data. Either we can get it directly from the ITS data, like total number of flows and what kind of vehicles are passing through different points in a road, and all the vehicle number plates are recorded, and from that we can actually do those determination, or we can actually do it as a part of the land use transport interaction modeling process, where we know that, okay, for how many link assignments, from the link assignment, how many vehicles will be actually plying along a particular road, and from that, and based on the travel times along that particular road, that means from where we get the speed and also the congestion and amount of time it spends in congestion, we can actually determine what kind of emission it will generate. So these are integrated emission traffic models. So, these are also used by many modelers these days. Now, coming to travel based emission models, here emission factors and travel data is used to generate emission inventories for a particular region, as we discussed. So, there are many models, of course, but the most famous is called the mobile emission factor model. This is the most widely used model. And then there is the emission factors model. In fact, this is for particularly used in California in US, and mobile is developed by EPA but actually used all over the world. And we also have this international vehicle emissions model, because this mobile and emission factors model, this has got huge data requirements. There are different vehicle technologies, different driving conditions and so on, which is not possible, we don't have, and which is not neither relevant for other developing countries, neither it is possible to get so much amount of data in developing countries. So, IV model was also developed as part of an initiative where the entire process was simplified in form of certain emission factors, certain correction factors, which could be modified or kept as it is, and based on that we can develop emission estimates for developing countries as well. But still it is it requires a huge amount of data that I will explain or show. And this model is again travel based. It is appropriate for developing countries, and different variants of this model has been used in India as well. And many people have developed other emission models in India as well, which is primarily follows the this particular this particular international IV model. So, then we have also got fuel based models, where usually a dynamometer based measure is used to calculate emission factors per unit load of fuel, per unit of fuel used. And fuel based emission inventories are first generated. That means we get from tax record or fuel cell record, we get how much amount of gasoline is being sold. From there we can actually determine, based on the different data that we have already generated based on dynamometer test, that for this much amount of fuel consumed, so much is the kind of emission. And we actually do different kind of cycles, that what is a typical how a vehicle operates and all, and based on that what is the fuel usage, and from that we can estimate. So, more or less the structure is similar to MOVE's mobile and mobile emission model, but it's instead of travel it is based on this fuel used. And then one of the models developed by European Environmental Agency, COPART, which is computer programmed to calculate emissions from road transport. This is one of the fuel based popular fuel based models that is in use, and suitable for and this kind of models is suitable where traffic survey data is relatively scarce. So, we have got so in addition to this kind of models, so we also have got something called instantaneous modal emissions model. So, and also microscopic traffic models and emission estimation. These two are more or less related with more detailed calculation of emissions from tailpipes of vehicles. And instead of having a very overall estimate, it gives us second by second tailpipe emissions are estimated as a functions of the vehicle's operating mode. Depending on how the vehicle is being operated, we can measure what is the emission coming out, and we measure the operation of the vehicle, and accordingly we get the result. So, one of the models in this particular this kind of model is comprehensive modal emissions model, CME, this one, and developed at the University of California Riverside. And then we have the Virginia Tech microscopic energy and emission model, VT Micro. So, this model is again based on chassis dynamometer data, which was used to calibrate the model, and it estimates fuel consumption, but the fuel consumption is done at real time, that how much amount of fuel is being consumed, and accordingly the emission is being estimated. And this model is also integrated with another model, which is named as integration. So, this integration model is basically a microscopic traffic model for an emission estimation model, and it actually shows that the total impact of traffic. So, in this particular model, microscopic energy and emission model, it estimates energy and emissions at different conditions of traffic, and as per a particular vehicle, and this is integrated with VT Micro, as we already said. And then we have this emission dispersion model also integrated with this particular model, and which actually shows that okay, once the emission comes out, how it is dispersed. It's a basic plume model that has been used over here. And impact of roadway grades on energy and fuel consumption is also measured. So this one is a microscopic model integration. This shows us at different kinds of traffic operation what kind of emissions are generated, and it follows the VT Micro model to estimate those emissions based on chassis dynamometer data, which has been used to calibrate those models. So then we have got transportation analysis and simulation system, TransSIMS model, which is an activity based model. So you will learn about activity based model in the you have already learned that in the previous lecture, but again you can have a detailed understanding of that in the last module, in module 12. And here in activity based models, individual vehicle could be modeled. We can determine the movement patterns of each vehicle, where it goes, which time of the day it goes, and so on. And based on those data, we can also estimate vehicle wise emission, or that could be also aggregated to a region wide emissions as well. So this kind of modeling system is also nowadays being used. And finally, we have got VISIM, which is part of the PTV group transportation suite, software suite, and where we do microscopic simulation. We have talked about this. So here we simulate every vehicle in the traffic stream, and not only passenger vehicles but also public transit. So here timely updates of how the vehicle is moving from one area to another, so and also how the vehicle moves in the stream, all these things are also recorded. So based on that, we can also, and if we give the emission factors for in this particular model, we can also estimate that, and for each vehicle fraction, of course, we can estimate the total amount of emission that is also being generated. So emission estimation based on instantaneous fuel consumption and tailpipe emissions, and can also estimate evaporative and accumulative emissions within a time interval. So VISIM is pretty robust in estimating the simulation for traffic in particular areas, like we have discussed earlier. And this emission factors, and also that if we can give the data for different vehicle fractions which is traveling in that particular traffic stream, we can also estimate the total amount of emission coming out of that particular generated because of those movements. So this is how microscopic traffic models are also nowadays being utilized for measuring emissions. So new emission models is also are being developed, and these are developed based on the PAMS technology. And this, for example, the model motor vehicle emission simulator MOVES. This is the latest model for from EPA, which is actually which is now a replacement for the mobile model. And this actually uses this PAMS technology. That means emission data is collected when the vehicle is in operation, and at different so when at different operation modes, we actually understand how the emission factors will vary, and that is being adopted. And this operation modes actually means different patterns of acceleration, cruising, deceleration, and average speed. So that means a vehicle is operated in different operation modes, and we need, if we know that, then based on onboard traffic onboard emission monitor, we can determine that okay, what kind of emission it generates, and that could be used to determine the emission for that particular vehicle. So mobile software uses aggregate driving cycles considering difference in average speed. So we considered that okay, for each driving cycle the speed is different, from that we estimate, but over here acceleration, cruising, deceleration, idling of the vehicle, all these things are considered, which was not considered earlier. So because the vehicle is sometimes stands in a parking lot, but the driver keeps the AC on and the vehicle engine on just to keep the vehicle cool. So that vehicle emission also needs to be estimated. So that is what MOVES is capable to do. So it can also estimate those emissions. So then as with the different driving cycles, we spend different amounts of energy, and that different amount of energy in a vehicle means different amounts of fuel is being consumed. So these are known as vehicle specific power, or VSP. So that means different amounts of energy is spent in different operating modes, and these are called VSPs, and this VSP data has to be estimated. So we calculate the VSP in as a equation which contains many of these factors of acceleration, deceleration and all these things, and from that we can get a composite figure which is used as a representation of that particular driving or that particular operation mode. So MOVES estimate total emission and energy use, and it does it for different kinds of vehicles, different kinds of cars, different kinds of trucks, buses, motorcycles and so on, and gradually it is replacing mobile for on-road vehicle emissions as the most popular model, or this is becoming standard. And it is both supports macroscopic, microscopic and mesoscopic analysis, and it can do estimation by hour, by day, both weekday and weekend, month, year, whatever is the time period we want, we can get from that. And it has a graphical user interface. It's built in Java, and it has got a database where, like MySQL is the RDMS relational database that is used in this particular model, because huge amount of data needs to be collected and stored. And the emissions are modeled, different kinds of emissions are modeled, like the running exhaust, that means when the vehicle runs what kind of emissions come out, the start exhaust. Usually in mobile, IV, this both start and running exhaust are measured, but along with that it also measures extended idling, evaporative processes and permeation, vapor venting, leaks. That means when at certain temperatures the fuel actually vaporizes and certain amount of fuel vapor comes out, which also is sort of emission. Then refueling displacement, refueling spillage, crankcase, tire wear, brake wear, and all these things. When you crank the vehicle, that also measures the emission and so on. So supports different kinds of road types and also vehicles of different ages. So this is a very, very comprehensive model, but as you can understand, it's very difficult to model this kind of get this kind of data for Indian conditions. So we have to do extended surveys to get this kind of data. So this is the international vehicle emissions model. So this is a variant of the MOVES model, and it is a standalone model with it's written in Java, and there are three essential input data that has to be put in. One is vehicle emission rates, vehicle activity, and the vehicle fleet distribution. So vehicle emission rate is basically the base emission for that particular technology, that particular vehicle kind and so on, and also different correction factors. That means depending on change in altitude, depending on change in many things, for example, depending on change of a particular technology, depending on change of use of air conditioner, we change the base emission factor. So this is one. Then the vehicle activity, that means depending on each location, the time, temperature changes, road grade changes, the inspection maintenance program is different, petrol and diesel is used is different, air conditioning usage is different, driving pattern is different, soak length is different, and this has to be considered. So this vehicle activity considers all these data inputs. Vehicle fit distribution is the total amount of vehicles of different technology, of different technologies, of different air conditioning systems involved, it's there or not, and base emission factors adjustment is done by this technology and as per different technologies of the vehicle, as per and also the pollutant as well. So these are the different three basic factors. So we can see there is a location in the model, there is location, there is fleet, and there is base adjustment. So these are the three components that data has to be put in, and then we can estimate the total amount of emission that comes out for this particular vehicular fleet. So the basic formula for this model is total emission produced for a particular area is base emission rate for each technology. There are approximately 700 technologies which are there in which is a combination of vehicle type, the engine, and fuel type, and so on. So this is so there are around 700 options to choose from, and so base emission rate for each of these option. Then each correction factor defined for each vehicle technology. So, we also apply correction factors, and then the amount of vehicle travel for each of this technology. So, you can see the correction factor. So, if I have this QT is the adjusted emission rate. Again, we have got two kinds of emission rate. One is the base emission, running emission rate, and the start emission rate. So, last time we were discussing in MOVs, so there is a start emission. So, when I start the vehicle, we get a certain kind of emission, and then when the vehicle is run, another kind of emission starts. So, when a vehicle starts, it actually gives out a lot of emission because of unburned fuel and so on. So, these are two measured differently. So, if I increase the number of starts, the number of the emission also increases. And running emission, there is standard, and then again depending on the speed in IV model, but in other models depending on speed, acceleration and other things, the emission actually changes. In IV model, we measure the average speed of different driving cycles, and accordingly we can also estimate the different emissions. So, these are the base rate, and this is multiplied by different factors. So, factors for temperature, factors for humidity, factors for inspection maintenance program, factors for fuel. As per that particular area's values, we will change the emission rate. So, adjusted emission rate is multiplied by, so once we done that, then we get an adjusted emission rate, which is multiplied by the travel fraction and the type of driving. So, that means for a particular fleet size, we break it into different fractions of different technologies and the driving habits for each of those technologies. So, both of that we will combine. So, this travel fraction comes from the fleet file that we showed in the previous slide, and we measure the running emissions based on this travel fraction, that is the percentage of time spent at each VSP condition. So, this is what, so that means time spent in different speeds, that will be actually combined, and we have the base emission rate. Because of running emissions, we have to convert it from grams per kilometer to grams per time. Why? Because we have to multiply with average velocity or the speed in that particular driving condition. So, we will convert it into grams per time from grams per kilometer. And for vehicle starts, that means for the start emissions, we just say units in gram per start. So, based on that, we measured that, okay, gram per time, how much the vehicle was operated in a particular way. So, we measured the emission, and also for number of starts, gram per start. So, total we get the total amount of emission coming out from different vehicle types. So, driving behavior and environmental conditions data specific to an area needs to be collected. So, this IV model has got data for many cities. Pune is also there. So, if we are not able to get data, collect data in our own city, we can adopt this particular data for the driving cycles and all. But as you understand, the driving cycle of Pune and Kolkata will vary, or Pune or Delhi will vary. So, for that we have to do more surveys. And what kind of surveys or data we require? We require data on driving behavior, like what kilometers we drive, the driving pattern, what is the average speed, acceleration and other profile, and the start patterns, the total number of starts, that means how many times you have to put on the vehicle and then put off, the soak pattern, the distribution of how long the engine has been resting when it is started. Then environmental variables like altitude, road grade, temperature, this also plays a role, and fuel characteristics like fuel quality and amount of contaminants and additives, this also needs to be also included in the model. So, these are the different data that we require, and as you can understand, we have to do this for different kinds of vehicles, for different technologies and so on. So, it's a huge amount of data that is required to run this kind of models. So, finally, what do we get? We get daily and hourly results for different criteria pollutants such as carbon monoxide, VOCs, evaporative emissions of volatile organic compounds, oxides of nitrogen, oxides of sulfur and so on, greenhouse gases like CO2, nitrous oxide, methane, toxic pollutants like butadiene, acetaldehyde, formaldehyde, lead, benzene, ammonia and so on. So, these are the different emission estimates that we will get. Now, once we get that, these are the total emissions for each of this particular gases or pollutants, then the next step is to actually model how they will spread in the atmosphere. So that is even more challenging, as I have already said, and we require specialists for that. So maybe there are environmental engineers who actually work in this particular field, but as a transportation modeler, we can end at the total amount of emission estimate, and some people do model the transport the resulting pollutant concentration as well. But resulting pollutant concentration is not only related with the total emission, it's also dependent on meteorology, it also dependent on background concentration, other emitters, and so on. So transportation emission dispersion impacts air quality and it eventually affects health. So that is true, and so we need to determine that. But again, sometimes it is the kind of data and the kind of expertise we require we require specialists for this. So pollutant concentration needs to be modeled for an urban area to determine exposure. Sometimes street canyons are affected more. So of course, people living in the surrounding major streets where there is a lot of vehicles passing are actually exposed to more amount of pollution. So we also need to understand how the pollutant concentration varies within the street canyons and then again outside. So there are different models for that. Some widely used models are the AirMod model. So this is California Meteorological Society and EPA Regulatory Model Improvement Committee model. So this is the AirMod. This is the most widely used model. Then there is a California. This is one of the most widely used model. Then California PUF, and then BLP, buoyant line and point source, and then this one is the most widely used. This is the California line source model or the CALINE model. So these are the models used usually for predicting line source emission. That line source, these are called line source model, not point source model. Whenever we have an industry and a stack or coming out of an industry, we have emission from that, we call it point source emission. These are called line source because this is lots of vehicles in a particular road. That's why we call them line source emission. So in addition to all these models, there is another model, operational street pollution model, OSPM. This is again an empirical parameterized model, and this is specially designed for urban street canyons and for modeling vehicular pollution. So this kind of models could also be used to estimate the amount of concentration of pollutants in a urban canyon as well. So this can handle specific meteorology and dispersion conditions inside street canyons and with buildings. So buildings on both sides. So accuracy of these models depends on accuracy of the emission data and meteorological data. So we require a huge amount of meteorological data to support this kind of models. So there are usually some pre-processors where we generate this meteorological data based on some inputs, and then those data is also used as basic input for this kind of models. So these are the different kinds of transportation pollution modeling software. These are used, and so in conjunction with estimation pollution estimates, we can also develop we can finally determine the pollutant concentration as well. So these are some of the references. So to conclude, this lecture introduces the various transportation emission measurement, emission modeling and pollution modeling technologies and software available to determine the extent and impact of vehicular air pollution in urban areas. However, most of this software are designed in developed countries, where unlike developing countries, data availability is not an issue. And the IV model designed for developing countries, even though used in India, suffers from data availability issues. And so there is a requirement for developing more robust model for Indian context. Thank you.